Hi, thank you all for joining another lecture for Introduction to Computer Graphics. Now, last time we completed our discussion on rendering related topics. The rest of this course, the rest of the lectures are going to be about computer animation. And computer animation is a huge topic. There are lots of things that are under the umbrella of computer animation. And today's lecture is going to be mostly about an overview of all sorts of different things that are under the umbrella of computer animation. And then in the following lecture, we're going to sort of dive deep on one of the topics under that umbrella. Right? So that's going to be our topic for the remaining lectures of this course. But before we get into computer animation, I would like to start with the discussion of video. Because we talked about raster images in quite a lot of detail, but we haven't really talked about video. And animation is going to be used for generating a video. Now, videos are not specific to computer animation. You can generate a video using your handheld camera or your phone or whatever. So this is going to be a discussion of, I want to start with a discussion of video, but even though this is not limited to computer animation, though it's sort of related to computer animation, I think it's important that we have some understanding of what video is before we talk about computer animation, right? So that's the preview of this topic. All right. So video. What's a video? You can think about a video as like a series of frames. Like there's one frame, and then another frame, and another frame, and another frame, and another frame, and so forth, right? And when we display these frames one after the other, overlapping like this, and we get something that is apparently moving. This is our perception, that we get something that looks like it's moving to us, although nothing is moving here, right? It's just one frame after another frame after another frame. We're just seeing still frames one after the others, like raster images one after the other, that sort of creates this illusion of motion for us. That's what a video is. So we have a bunch of frames displayed super quickly, one after the other. Now, the immediate question, I think, when you look at the topic like this, is how fast I should be swapping between frames. I think that's the first question, right? So, how many frames per second should I be displaying? Now, you might think that there's a standard for it, and you would be partially right. And there are standards, but there isn't a single standard that sort of applies to all sorts of video that we have. There are a whole bunch of standards. So, for example, if you think about broadcast TV, the standard that we have, at least in the US, is the NTSC standard of 30 frames per second. So that's how broadcast TV is displayed in the US. But it's not everywhere else on Earth. In Europe, for example, we have a different standard that uses 25 frames per second. Now, you may think, oh, 30 frames per second is greater than 25 frames per second. That's great, right? For US TV is, you could say, argue better. But let's talk about movies. In movies, the standard is 24 frames per second. So that's the standard. Although, sort of, usually there's this trend that there are some high frame rate movies that can have 48 and even 120 frames per second movies are out there. Some people like that high frame rate stuff, and some people don't like it so much. They kind of like the old 24 frames per second standard because that generates a bit more motion blur and more softer animation. So, it's a matter of preference, but that exists, and 24 frames per second is the standard that people use. All right, that's for movies. How about our computers? Now we're generating all sorts of images and animations with our computers, right? So what do we show on our computers? For computer monitors, we typically refer to how many frames we display per second as like the refresh rate of a monitor. And the refresh rate is measured in hertz. Hertz is 1 over second. It's basically 1 hertz is 1 frame per second. So a typical refresh rate is about 60 hertz. Typically, monitors don't go below 60 hertz, but they can. It's possible. But that's typical. That 60 hertz is probably the sort of general standard. But you can have monitors that are much higher frame rates than 60 hertz. It could be 120 hertz monitors are actually quite common. They're not uncommon at all. They give you a better image in that perspective, like better animation because the refresh rate is higher. How about video games? Well, video games should probably follow the standard of monitors, right? If my monitor is displaying 60 frames per second, then probably in a video game, I should be generating 60 frames per second, right? And that kind of follows with that. So typical video games today are around, they target 60 to 120 frames per second. But depending on the type of images that they're rendering, sometimes they can't really keep up with that. Depending on what hardware you're using for rendering those images, maybe they fall below 60 frames per second. That's not desirable, but it can happen, right? So if you crank up all the rendering parameters of your game, then maybe your computer won't be able to keep up with 60 frames per second. But they typically target 60 or 120 frames per second, and high frame rate is oftentimes preferred. So these are the sort of standards for video frame rate, and they vary quite a bit, as you can see. So this video that you're watching right now, I'm trying to broadcast it at 30 frames per second, following the broadcast TV standard. But who knows what we're actually receiving? But that's what it's supposed to be. So that's the standard that I picked for this. All right, so another thing that you might think about is video resolution. That's the resolution of each frame. I'm talking about the raster image resolution that we're using for each frame. Now, resolution is sort of, the first thing to think about is the aspect ratio, like the ratio of width and height of the image, right? The typical aspect ratio in the past was 4:3. So most of our displays were 4:3. Most of the TVs were in this aspect ratio, and so we use that standard. And VGA standard that was released in 1987 was using this 640 to 480. That was the screen resolution for VGA that we've used for quite a while. And today, a lot of people refer to this as like the standard definition. Standard definition resolution would be this VGA. But pretty quickly, this was replaced by XGA, this 1024 by 768. This was a very, very popular resolution that has been around for quite some time, from 1990s. And it's been used a lot, actually. This was a very, very popular resolution. But today, when we think about today's video standards, we typically prefer a different aspect ratio. We typically prefer 16 by 9. So this is closer to the aspect ratio used in movies. So that's what we prefer today. You can have various resolutions, but the standards that most people use are, there's a 480p resolution. So this is very low resolution videos. As you can see, this is the same resolution as the standard definition in terms of height. The width is a little bit wider because of the aspect ratio, right? The different aspect ratio. If you go to a high definition video, we have 720p as higher resolution, and we also have 1080p. That's also called high definition as compared to standard definition. Also, on top of that, we have 4K, right? That's Ultra HD, and also 8K is around, not as frequently used, but it's there, another Ultra HD resolution. So if you were to compare these, like what do they look like in terms of pixel size? Whenever you display a video, you probably display that video full screen. So if you're watching a video in low resolution, your pixel size of your video is going to be much larger than playing a video in high resolution. Nonetheless, if you were to just display them in their native video size resolutions and keep the pixel size the same, and put these different resolutions on top of each other, this is what it looks like. Whoa, it's blocking me. So, as you can see, SD is way at the top there, and then 720p, 1080p, and then 4K and 8K, right? 8K is significantly larger than the others. And if you're wondering what XGA looked like, it's sort of a little bit larger than That's the dashed lines over there showing the exchange resolution. Its height is a little bit more than HD 1020p. Its width is not as much. It's a different aspect ratio. All right, so these are the typical resolutions that people use for displaying videos. Now, I want to talk about video data as well, right? So this is actually a video is massive amounts of data. So if you don't quite appreciate it just yet, let's see what that will look like. So let's say that I'm displaying a video with just RGB colors. And I'm not going to go into high bit rate here for displaying colors. I'm just going to use 8 bits per channel. That means I have 3 bytes per pixel. Alright, so this is, you know, you really probably shouldn't go below that. And let's say we pick a typical sort of HD video. That's sort of reasonable today. And that would mean that I have about 900,000 pixels to display, right? Per frame. So that would make, if it's 3 bytes per pixel, that would be like 2.8 megabytes per frame. And if I'm displaying a video in 30 frames per second, that would mean about 83 megabytes per second, right? So if you were to watch a video like this, like if you're streaming a video like this online, you need an internet connection that has 664 megabits per second. I doubt that any of you have this sort of an internet connection. That would be that would not be so easy to consistently get this bit rate from your internet connection, right? And this video actually is not in 720p resolution. This video that you're watching on YouTube, you should be getting 1080p. That's what I'm using to broadcast. In 1080p, these numbers go up quite a bit. So in 1080p, if you were to actually listen to this with raw data, that would be, you need something, internet connection of 1.5 gigabit per second, which is sort of a little too much, right? So how on earth are we getting this video when we don't have such ridiculous, internet connection speed? The reason that we can do this is video compression. Now, video compression is very, very vital to all sorts of video broadcasts. So just a really brief overview of how video compression works. So we have a bunch of frames, frame 1, frame 2, whatever. We have a bunch of frames displaying video, and we can compress each frame, and you get compressed data. So you don't need to send the actual image up here. You just need to send the frame data that sort of represents what this image looks like. So this is a lot smaller than this, right? That's how we're getting it. So each frame can be compressed like this with a compressed data. But there's another very, very important thing, very, very crucial thing. For most video frames, from one frame to the next frame, the difference between the frames typically is not that much. Like when you look at these 2 frames, for example, I mean, yeah, they are different, but they're not all that different. There's lots of similarity between them. So if you don't compress each frame independently, but you sort of combine the data, because if I send the data about the first frame, that kind of gives me an estimate of what this next frame will look like, right? So and I just need to know how the frame changes from one frame to the other. So if you use that information, you can actually compress this data quite a bit more. So the data that you will need for representing the next frame becomes a lot less because you're sort of using the previous frame as your baseline. So that's the very general idea of video compression used in various video formats. One example for that is probably the most popular example today is the MPEG-4 and H.264 is the a standard codec for this. So we don't call it compress, we typically call it encode. So you take a raw video with RGB data and you encode it into whatever video format that you're using. And then at display time, you just take that data and you decode it, right? So you decode it and that's what you watch. So what's happening right now is that as I'm broadcasting this video, my computer is on the fly encoding this video and then broadcasting just this data over the internet, and you guys are downloading this data and decoding it to show it. Now this decoding happens very, very often. So this needs to happen sort of efficiently and quite fast. And we can do that efficiently and fast because we actually have dedicated hardware on our computers handling this video decoding. And that's how we can do this power efficiently and also quickly enough, right? So that's a very, very important part of video compression and decompression. All right, so this is all I want to say about video. As I said, this is very general. I haven't said anything about how these frames are generated. So these could be coming from my handheld camera, or it could be coming from some computer animation sequence that I generated. Of course, this video compression stuff is applied to video that is sort of either broadcasted or recorded. If we're talking about video that's generated real time, then we don't necessarily have to think about compression, decompression. There is compression, decompression on the GPU for other purposes, for sort of accelerating the process of generating the images. But for displaying the images, we don't need to worry about this stuff too much. All right. So some of this applies to computer animation, but not all of that applies to computer animation. I just wanted to cover this topic a little bit before we get into our main topic, that is computer animation. All right. So the first question: what is animation? Now, animation can be a lot of things, but I sort of classify this into two groups. One could be just a simple transformation. So if I have an object and I change the way that I transform this object, so that could be one way of animating it. Like in this example, I just moved my object to a different position and it slowly moved, and that was the animation, right? You watch the animation. That wasn't very exciting though, but sometimes this is exactly what you want and what you need, and that's good enough. And that's fairly easy to do because all I got to do this is to change the transformation matrices, right? So I had a transformation matrix for this object and I just change it to another transformation matrix, and that sort of defined my entire animation. Simple enough. So if I have a rigid motion like this, that's easy, and I'm going to call it transformation. The other kind of animation can be deformation. Now, deformation can be something simple or can be something quite complicated, right? So if I were to apply some deformation to this character, I could actually represent a whole bunch of interesting motion and interesting animation, right? So, and all of this is done through sort of deformations of the surface that represents this object. And that's, as you can see, is quite a bit more complicated. It's more complicated to process, it's more complicated to actually define. So it's much more complicated to specify. Like, how would you specify an animation like this? And that's going to be basically our main topic. Like, how do you define some sort of animation that might involve deformation? Now, so that brings us to our second question: how do you specify animation? Now I'm going to talk about how to specify animation in 4 different topics. It's going to be procedural animation, keyframing, motion capture, and physics-based animation. I'm going to go through the first 3 of them today, and the last one I'm just going to briefly mention, and we're going to talk a lot more about this one in our upcoming lectures. Alright, so let's talk about procedural animation. Now, the simplest form of procedural animation, I think, is going to be just some transformation function. So I am writing some mathematical function or just some algorithm that changes the transformation function. What can I do? For example, I can just rotate this teapot, right? So something very, very easy. We had a procedural animation of rotating teapot in one of our earlier projects. You'll remember the rotating object, whatever object you loaded in one of our earlier projects. We had this. So fairly easy to do. All you need to do is to change the transformation matrix. You just change the rotation parameter here and you're done, right? Very, very easy to do. But of course, there isn't much you can do with this. But procedural animation is not limited to just transformation functions. We can also have a deformation function, right? So we can apply some mathematical formulation that deforms our object. In this case, I am deforming a teapot. Hey, I'm free to deform the Utah teapot. Why not? I'm Jim Blinn squished the teapot and gave it its shape that we recognize it today. I'm okay to bend the teapot now, and that's exactly what I'm doing now. So this is a procedural function that bends the teapot. So the exact mathematics of this function is not too important, but it's not a very complicated function. It's a very simple function that deforms. And I am changing how much deformation is applied to this teapot by changing the deformation parameter. And I'm using a sine function here to change the deformation parameter. So it just keeps rocking like this because it's bending back and forth. Yeah, so fairly simple function, fairly simple procedural function that does this. Now, don't get me wrong though, procedural animation does not have to be something simple. It can be something simple, a simple example like this. It can be something a bit more complicated. Now here's another example, something that I've done back in the day when I was a grad student. This is procedural animation. It's just code doing this thing that I thought was funny back then. I still think that it's sort of funny. So like all of this motion, the frog here pumping and the gears cranking here, all of this motion is handled by some procedural functions. Right? It's basically all math and nothing else here that's giving us this motion. So just to say that procedural animation can be more complicated. In fact, one common way, one common method that could be considered under the umbrella of procedural animation is flocking. Flocking is the idea of controlling a whole bunch of objects, multiple objects, forming a flock, moving them together. It's typically handled by using some sort of procedural function. And that procedural function can be something a bit more complicated. So it doesn't have to have, so you don't have to have a function that defines the entire motion from start to end. This flocking function can be something that's defined like one frame at a time. So at every frame, you define what's going to happen to all objects inside this flock for the next frame. I'll show you an example of this. So here's an example. I thought it was pretty cute. I love this. So in this case, all these red objects here are sort of in some way following the blue one based on some procedural function. So this is an example of flocking. There are a whole bunch of examples of flocking that's actually used a lot in computer graphics. And as you can see, it can generate some really interesting, compelling animations. It's a fairly useful tool for generating all sorts of animations. Right. But we still haven't quite talked about how we could possibly get that dinosaur animation I showed you earlier. Right? So to be able to generate something like this, we need to talk about keyframing. So the idea of keyframing existed for a very long time, way before people were worried about computer graphics. People use keyframing for hand-drawn animation too. So let's say that I have these 3 frames sort of defining an animation. So when you look at these 3 frames, I think you can have some idea about what's going on in this animation, right? So the character was in this pose and then moved to this pose and then this pose. But if I were to display these 2 frames one after the other, it won't quite look like a smooth animation, right? It will look sort of jumpy because I need more frames in between them here. Right? So the way this works is that I'm going to use a few like hero frames as frames that sort of define the animation. I'm going to call them keyframes. To be able to generate a smooth animation, I'm going to need the frames in between them. So I am going to use these frames and I'm going to generate the frames in between them. And those are typically called tweens, or in-between frames. This idea of keyframing, as I said, existed for quite some time. Like back in the day for hand-drawn animation, your lead animator would be the one drawing these keyframes. And then all the other people will be drawing these in-between frames that connect one keyframe to the other. And today, we use computer graphics a lot. Instead of having an army of people drawing these in-between frames, we would use all sorts of computer graphics tools to sort of automatically or semi-automatically generate these in-between frames. That's the idea of keyframing. By using the concept of keyframing, I don't have to specify each and every frame independently, because that would be a ton of work, right? So whatever animation that you're trying to produce, if you were to generate, let's say, 30 frames per second, and if you were to manually create these frames for any animation, that would take a very, very long time. But if you were to create only a few hero frames that sort of define the animation, and if your computer could automatically generate these in between frames, then it would save a lot of time. So that's the idea of keyframing. That's used very, very often, very frequently in computer graphics. So most animations that you see will be probably some form of keyframing. Right? That's the main tool used for generating all sorts of animation in computer graphics. So because of that, I would like to go into a little bit of math, not too much, just a little bit, right? So let's say that I have two keyframes. I have one keyframe and another keyframe here, and I am going to generate a smooth animation from one keyframe to the next keyframe. Now my first keyframe defines, let's say, some set of positions. I'm going to call them x1, something. x1 can mean anything. It just means, let's say, the shape of my object at time t1, right? And x2 defines, again, the whole set of parameters, the shape of my object at time t2. And I'm going to interpolate the shape of my object from x1 to x2 as time goes from t1 to t2, all right? That's the whole idea. So what can I do? The simplest thing I can do, I guess, would be some sort of linear interpolation, right? So keyframe interpolation could be linear, and this is a very simple linear interpolation function, right? So think about these as vectors. The positions, the shape of my object at any time t would be a function of x1 and x2, and I'm just adding the difference between x1 and x2 based on where the time is between t1 and t2. Anyhow, that's the linear interpolation function. I can do something better. I can do, for example, smooth step instead of doing just a linear interpolation. So I can vary the position between t1 and t2, like the deformation of my object between x1 and x2. I can smoothly deform from one shape to the other shape, right? From x1 to x2, I can smoothly deform. And this is a typical smooth step function. There are others as well. When a is 0, this function becomes 0. When a is 1, this function is 1. So basically, it's not linear. It sort of creates this smooth interpolation. Right. So I can use something like this, and then my motion would be somewhat smooth. So let me show you an example. Let's say that my position at x1 is this. And then x2, I'm moving to another position. Now, did you pay attention here? Pay attention to the motion here. So it starts slow and then it slows down, right? It starts slow and then it slows down. It's not moving with constant speed. It's sort of slowing down as it reaches this next motion. And it's all done by sort of slowing down how fast the deformation moves from x1 to x2 by using this smooth step function. Let's say that I have another keyframe after this. Let's call it x3. So in this case, I'm sort of smoothly moving from x2 to x3. But this does not actually create a smooth animation. I'm not sure if you've noticed, but this is not a very smooth animation. Yeah, it's smoothly interpolating from one frame to another, but the animation is still linear, right? So we started from x1, and then we moved to x2 along this line. And then from x2 to x3, again, we're moving along this line. So we came from here to here, and then we sharply turned and moved in this direction. So the motion is not smooth. Yet the interpolation between frames is smooth, but the motion itself is not smooth. If you would like the motion to be smooth, then we should probably put that motion along a curve like this, right? So for example, I could use something like a Kaplan spline to generate a curve like this, and then I can compute the positions along this curve using these control points, keyframes as my control points. Of course, a cubic Kaplan spline would need another control point. I'm assuming that there's another control point here, and that would be a function of these control points, right? So, yeah, you don't have to use Kaplan spline. There's a whole bunch of different things you can do here. I'm just giving you an example. A couple multiplying could be really nice for defining a smooth interpolation between keyframes. So this is a very, very important thing. And typically what we do with keyframe animation is that we specify these keyframes and we specify where we would like our object to be at any time that we want. So we specify the time and the position or shape of our object. And then we also specify what kind of interpolation we want between keyframes. And the rest is done sort of automatically using some mathematical formulation. Fairly simple mathematical formulation. And how do we specify these keyframes? Well, we use all sorts of modeling tools. You move vertices one vertex at a time, you give your object a shape, and you say that my object is going to take that shape at that time along this timeline. Right. So, but generating some complicated shapes for our keyframes here can be rather complicated. To make this process a little bit easier, we use different tools. For example, a very common way of specifying keyframes would be something that we call morphing or blend shape interpolation. So here's a video. This is the concept of morphing or blend shape interpolation. So the way this works is that, let's say I have a model. I create different versions of this model. So I just take the vertices and move them around, and I create a blend shape. So in this case, it's showing a bunch of blend shapes that are already prepared by the modeler, whoever is preparing them. And then what these sliders are doing is that it's interpolating the base pose and one of the target poses. And you can combine multiple poses together, like in this example. So a little bit of one pose, a little bit of the other pose, and you combine them together, just a weighted average of these poses, and you get an in-between shape like this. So that's a way of animating models. These blend shapes are used for specifying keyframes, and I'm going to generate different keyframes using different combinations of blend shapes. And then my interpolation is just going to interpolate the blending weights of different blend shapes, right? So I'm going to interpolate the blending weights, and then using the interpolated blending weights, I can compute the in-between poses between these keyframe poses. Right? So that's the idea of morphing or blend shape interpolation. Very, very useful idea. And I'm showing you this example because it's typically used for facial animation. It's actually very, very useful for facial animation. But it's not as much useful for animating a whole body. Because, human body and, most animal bodies are not like squishy and soft. So we have a well-defined skeletal system, so it kind of makes sense to use that skeletal form. And that brings us to skeletal animation. So the concept of skeletal animation is that I first start with defining a skeleton for my model. Whatever my model is, I define a skeleton for it. And then the skeleton, the shape of that skeleton, is going to define the deformation of the surface that's attached to the skeleton. This is called skinning sometimes, like attaching a skin to a skeleton. I'm just attaching a surface to a skeleton, right? And all I got to do at this point is to define how my surface is going to deform as I'm deforming my skeleton. Now the skeleton is defined by these bones and joints. And typically, as you would expect from a skeleton, I define the motion by rotating these joints. Right? There are different ways of defining this skeleton. A lot of times people prefer using inverse kinematics. For example, I can specify exactly where the hand is supposed to be, and inverse kinematics computation figures out what the joint angles are supposed to be so that the hand is exactly at that position. Or I can use forward kinematics, in which case I specify the joint rotations, and that gives me a position for hand or feet and so forth. This is a typical concept of skeletal animation. And as you can see, in this case at least, this skeleton is a lot less complicated than the actual skeleton, right? So it is sort of simplified form of a humanoid skeleton. And that sort of makes sense because we don't necessarily need to worry about all sorts of detail, all sorts of bones that we have in our body. So it kind of makes sense to have fewer bones here, so we have fewer parameters to worry about when we are animating this model. So in that sense, the fewer the better. But at the same time, when you have too few bones, that sort of limits the types of animations you can generate with this skeleton model. So you want to have enough bones here, enough joints to specify the animation that you want, but you don't want too many of them because you don't want to deal with unnecessary complexity when you're defining the motion. And a lot of times people generate special controls, and sometimes they generate high-level controls for controlling a bunch of bones altogether. So I can have another control here that says just bend the spine forward a little bit. So instead of bending all of these bones one by one, I can have one control that uniformly bends all of them at the same time. So there are different levels of controls people can generate in this process of generating a skeleton for a model and then attaching that skeleton to a model. We call that rigging. All right? I'm going to show you an example of rigging in a little bit. So with skeleton animation, as I said, I had one pose and I'm generating a different pose using this skeleton. So like this bone moves over here and this other bone moves over there. So just a rotation transformation. This is rigid transformation, something that we're familiar with, something that we know how to do. Now the question is, for each vertex on this model, how am I going to move this vertex based on the deformation of these bones? Now this particular vertex that I'm showing here over there is sort of in between two bones, right? So it's going to be impacted by the bone over here and the bone over there, right? It's going to be impacted by these two bones. We typically define some sort of weighing function, some weight that specifies how much each vertex is impacted by the bone motion. So in this representation, red means that it's like fully impacted by the bone motion, and down to blue, it's like very little impacted. Over here, this particular bone does not impact these points too much, but over here, it just completely defines how these vertices are moved. For our vertex in the middle, it has a particular weight, and it has some other weight that corresponds to the other bone. So as I'm moving these two bones, combination of these weights will give me the resulting motion for this vertex. Now this seems very simple. I can just linearly blend the motions, and that's called linear blend skinning. That's used for all sorts of animation, but there are other methods. There are some nonlinear methods that provide better forms of deformation, especially when you have significant deformation of bones. But I'm not getting into the mathematical details of that process. But the idea is still there. It's just you sort of combine the motions of these bones in one way or another. Now, what I'm going to do is that I'm going to show you an example of rigging of a particular model here. So in this case, it's a horse model, and it has a bone structure that you can see. This is a student demo showing what kind of animations you could generate with this particular rigging. As you can see, this is not just bone motion, but there are other things involved. There are some high-level controls there as well. And so this allows all sorts of different motion that can be generated by this type of rigging. Right? So this is what you typically give to an animator, a model that is rigged, and an animator would specify the poses, the keyframes, by controlling the parameters of this rig. And then, of course, what we'll do is that we're going to interpolate between these keyframes, and that's how we get keyframe animation. So, as you can see, there are a whole bunch of controls here for all sorts of different motion. Alright, I'm not going to show you all of this. I think you get the idea. Right. But nonetheless, there's so many controls. So it can be kind of difficult to control this precisely to get exactly what you want. Like, as you can see, it's a lot easier than controlling each vertex one by one, but still there are lots of control points, right? So for generating an animation like this is still a very labor-intensive process, and that brings us to motion capture. So one way we can make this process of generating an animation easier is to use motion capture. So with motion capture, we don't actually even have to use keyframing. We can specify each frame separately because it's all automatic. So what we do with motion capture is typically that, for example, for full body motion capture, our actor is going to wear a motion capture suit that will include some markers on the person's body. And with using these markers, we can estimate the bone motion. Now, the word estimate is very important here because we can't capture the exact bone motion because all we don't see that person's bones, right? We can see what's outside of the bones. We can only see the skin and the markers on the skin. The markers on the skin are helping our computer vision process to get the positions of these markers accurately. Unless we use X-ray and not worry about the health of this actor, we won't be able to see the bones pretty clearly, right? So we need to use different sorts of algorithms to estimate the orientation of these bones based on what we can see. And we have pretty good algorithms today that do a very, very good job of estimating these bones. There's going to be some error associated with it. There's going to be some cleanup. Sometimes there's going to be some manual cleanup. Sometimes there are automatic algorithms that sort of clean up the error in the estimation. But I just wanted to clarify that this is not like a foolproof, completely perfect way of generating motion, but it is used a lot in practice. A lot, actually. In video games, it's used a lot. In feature animation, it's used, and especially in special effects, it's used so much that it's a very, very standard technique. And we have tools that can generate very clean animation from this. And if it's not clean enough, then the animators will go in and manually clean this. But at the end of the day, they don't have to start from scratch. They start with something that comes out of motion capture. So you can pretty quickly define some motion, and very realistic motion too. So if you don't use motion capture, if you just use keyframing by this rig model that I showed you earlier, generating a realistic motion out of that can be quite a bit of a challenge. But with this, it becomes significantly easier, significantly less time consuming, and that's why it's a very, very popular technique that's used in computer graphics today. Now, this is good for capturing skeletal motion. For facial animation, we use different methods. So I'm going to show you an example here from a relatively recent CGRAPH paper that's doing a great job in capturing facial animation. As you can see here, this particular algorithm is capturing the surface and not just the motion of the eyes and the lips, but also wrinkles. Wrinkles are captured here as well, and the motion of wrinkles are captured. In fact, this particular method works in real time, so you can just sit in front of your camera. It's just from this image, it's estimating the expression, the shape of the subject's face, and it's it's even able to capture different people's faces like this. And this sort of techniques are actually quite commonly used in production, as I was saying. They use for generating cinematics or cinematic animations for video games, are also used in special effects quite a bit. So in this example, the actor is wearing a full body motion capture suit, so that's how they capture the full body. And then the suit also has a camera that's fixed in front of the actor's face, so they're capturing the actor's facial motion as well. And by using that, they can fairly easily transfer that motion to the motion of a different character. So there are all sorts of algorithms here. So it's not just about capturing the motion of this actor accurately, but also this actor has a certain skeleton type, and certain facial features. That's also the problem of how you take that motion of that actor and then transform that motion to a different skeleton, a character with a different skeletal proportions, and a character with a different facial shape. And so there's this whole motion transformation is happening here as well. There's a bunch of algorithms that run in the background that handle that as well. So it's another fairly big topic in computer graphics, how to do that properly. I'm just acknowledging the existence of these problems and there are algorithms for these. I'm not getting into the details of how any of this is done. But I just want you to know that these sort of problems exist in computer graphics, and we have algorithms that do that. Now, another big topic in computer graphics that we're going to talk a bit more extensively on is physics-based animation. So we can do a lot of things with the other animation tools, but sometimes we have motion and deformation of objects that are so complicated that we really don't want to do those by hand. And what we prefer doing in that case is we use some physics-based animation. We actually compute the physical rules of how objects sort of interact with each other, how those objects move in the physical world, and sometimes call it physics-based simulation or simulation. And we're going to talk about this extensively. I'm not talking about it too much, but I would like to show you one example from my recent research. Now, this is something new from one of our recent paper submissions. So in this case, there's fluid animation. Again, fluid animation with some fracture simulation. The other one included some cloth simulation as well. And we're going to look into the details of physics-based animation, not to this detail, not to this extent, but the particular technique that we're going to explore in more detail is going to be the underlying technique that's used for this fracture simulation over here. We're not going to do a fracture simulation. That's a bit more complicated, but we're going to see the fundamental concepts behind generating an animation that looks like this, right? So I'm not going to go into more detail today. I'm going to do that next time, right? But today, I want to end this lecture by showing you this video. I think this is a nice example. I kind of like what it looks like, but the point I'm trying to make here is that computer animation is a lot of times generated not by one of these methods that I mentioned, but a collection of these methods. So over here, I believe there's some motion capture going on with the running motion. I believe it's motion capture. It may not be. I'm not sure, but it might be. There's definitely physics-based animation here. There is some procedural animation that's controlling the behavior of this crowd. So there are a whole bunch of methods intertwined together to create this sort of humorous animation. And that is actually quite typical. That a lot of animations that we see can be a combination of various different animations. But it doesn't have to be. Sometimes just keyframing is good enough. So that dinosaur motion I showed you in the very beginning was just keyframing, and that can be sufficient as well. But for more complicated motion and a whole bunch of characters like this, we prefer using different techniques. In this case, physics-based animation and some procedural animation is combined. All right, so that's what I plan to talk about for today. So this was a brief overview of the kinds of things that are under the umbrella of computer animation. Next time around, we're going to dive deep and talk about physics-based animation in more detail. We're going to actually explore one particular way, one particular method in physics-based animation. And our upcoming project, Project 7, that's going to be our last project, is going to be about that physics-based animation technique. All right, that's what I plan to cover for today. Do you guys have any questions or comments or anything about the stuff that we covered so far? How is fur usually animated? That's the question. We typically use physics-based animation for fur, but not always. Sometimes different forms of procedural animation can be good enough. We don't necessarily have to really going into physics-based simulation of fur. But oftentimes when you see an interesting motion of fur that uses some form of physics-based animation. But it can be just procedural as well if the motion is relatively simple. Just some procedural function can be sufficient. Any other questions, comments? Okay, then I'm ending it here. I'll see you next time when we talk in more detail about physics-based animation. Thanks and bye.